to our first invited speaker, who's Gábor. So he's going to be talking about detection of correlations. Yes.
Thanks very much for the invitation. It's a real pleasure to be here for many reasons. So today I'm going to tell you about ongoing work with several co-authors, mostly with Sebastian Bubeck, who is in Princeton now, and Arias Castro, who is in San Diego. And we are interested in a detection problem, and which I will describe you in detail. Let me start with a motivating example that was the driving force behind all this work. Let's say that we send out satellites to outer space, and these satellites are collecting data, and we want to detect if there's something ominous coming at us. Okay, so. Normally, if there's no attack, then the satellite just picks up noise, and this noise is modeled as white noise. So I will assume that if nothing happens, then the signals are just IID Gaussian, standard Gaussian signals. Okay, so this is our null hypothesis, and the alternative hypothesis is there's an attack, but we want to detect this attack really quickly, and when the bad guys, the bad spaceships, are really far away, and maybe very few of our satellites are picking up signal. Okay, so this will be a detection problem when the signal is weak and sparse, and basically what we want to understand is when is detection possible. So how weak, how strong the signal has to be, and how many satellites need to pick up that signal such that we can ring the alert bell. Okay, so here's the model. If there's an attack, then there's a small subset of the satellites that receive a signal which is still covered in this noise. Okay, so the alternative hypothesis is that there exists a subset of the components of our observation vector, such that over those components we have a common signal. This YT, these are also modeled as standard normal, but this is common for all the eyes. Right? This YT doesn't depend on the index. And otherwise, we have white noise, which is independent for all these satellites. Okay? So this is the detection problem. Okay? So let me say it again, because this is what the whole talk is about this detection problem. Under the null, we want to decide whether there's signal or there's no signal. Under the null hypothesis, there's no signal, everything is standard normal. Under the alternative, there's a small subset, which we don't know which subset. There's a small subset of components of this observation vector, such that over those components, there is embedded in noise, there's a weak signal. Okay? So these YTs are standard normal with variance rho. So rho is one of the crucial parameters. Another crucial parameter is the size of this set, which I will denote by K. Okay? So we want to know how large K and rho have to be such that we are able to detect. And the two important parameters here are N, which is dimension, and D, which is sample size. So we receive signals for each time instant, and this goes for D times. Okay? All right? So here's the mathematical description of the problem. We observe these D IID vectors vectors. I have to apologize because in this talk n is dimension and d is sample size. But you can look at it another way, and at the end of the talk we will look at. So basically our data is a matrix, is an n by d matrix, and you can look at it two different ways. Okay? But let's start it like this. So we have d observations of d vectors of size n, and typically this n is much larger than d. Okay, so this is why I call this a high-dimensional detection problem. We want to detect really quickly, right? We don't want to wait until we have very hard evidence. We want to ring the bell as soon as possible, right? So d is time. We want to detect very quickly. So we observe these observations, and the null hypothesis is that the components of these vectors are independent. So this should be a D here, I'm sorry. This is just bad habits. So under the null hypothesis, these components are independent. And under the alternative hypothesis, there's a small subset which we don't know of the components that are contaminated by signal. Okay? So in other words, we observe a Gaussian vector under the alternative hypothesis, and the covariance matrix of this vector looks like we have ones here, and we have zeros almost everywhere, except that there's a small subset of the components, such that over these components we have these rows sitting here. Okay, so we have a small submatrix where we have this common signal. Okay, all right. But we don't know where they are, and there are very few of them, and then this row is usually small. Right. So how can formalize what do we mean by we're trying to detect? Well, we are doing tests. A test is just a function that takes all this data in and outputs 0 or 1. Okay? 0 means that 1 means the test thinks that there is an attack. Okay? There are various ways of describing the quality of how the test is. One way of defining a risk for the test is just add the type 1 and the type 2 errors. Okay, of course, there are various possibilities here, but I want to keep the formula simple, so we will mostly talk about this function. So what it is the probability that under the null, given that all these vectors are IID, standard Gaussians, that's P sub 4, are tested as well. So this is a mistake. There's probably a false one. And this is if set S is the contaminated set, then this is just the probability distribution of such a Gaussian. Okay, so that's P sub S, but we don't know what the set is, so this is a kind of a Bayesian perspective. Okay, so we suppose that one of the sets is selected by random, and we just average the probability that we think that there's no attack, there is an attack. Okay, so if you write it like this, then this is just a usual hypothesis testing problem between two alternatives. One of the alternatives is that the distribution is standard Gaussian, and the other alternative is that the distribution is a mixture of these guys. Mixture of ancient K Gaussian distributions of this type, because that's how many possible subsets we have. Okay? There's another way of measuring this, which is with a worst case. So I'll make this so that you can see better. We look at the maximum over all subsets of X. But it turns out that these two risk measures are closely related. So if you don't like the Bayesian perspective, you don't like to think that someone picks at random the attack, the subset S over which the attack comes, then you maybe want to prepare for the worst case, and then this is a natural way of measuring things. If the function f, if the test is symmetric, then these two will be the same actually, and in any case, Rf is always less than or equal to R bar of f. So there's a simple relationship between these two, and we will see that all our lower bounds will be for Rf, all our upper bounds for R bar of f, and sometimes these will be close to each other. So these are two natural ways. Turns out that for deriving lower bounds, this is somehow easier. For upper bounds, this is easier. Okay. So the nice way, the nice property of working with this Bayesian risk is that we can actually determine the optimal test, because this is just a usual classification problem with two distributions. One of them is a standard Gaussian, the other is this awful mixture distribution. So we can actually write down the likelihood ratio test. Okay? Then we know what the optimum test is. Okay? What we don't know is how good this is. Okay? Also, we know how to compute it, which is a serious problem. So we know that the likelihood ratio test will be we look at the ratio of, let me write, x. And now this x is all our impact observations, and this is just the standard normal distribution. And instead, we have this mixture of indices of phi sub s of x, where phi sub s is the Gaussian density with this covariance matrix. This is the likelihood ratio, and we just, for each x, we just have to calculate whether this is greater or this ratio is greater than or not. Right? You know the elements. The likelihood ratio, and this is optimal. This minimizes the risk. This is a statistical movement. The problem is that if n is large and k is not too small, then we can't calculate this test. So the optimal test is not easy to calculate and also not so easy to analyze. Okay, we are interested in both. So I will mostly talk about how to analyze this, but I will also spend some time on I think is a very important and very sexy challenge, is how to come up with good tests that are computationally feasible. This looks like a major problem in this field. Okay, so here's the lower bound. This is true for all these and k's and rho. Okay, so the probability of the likelihood effect is always greater than this right here, which involves rho and d and k and n. You can see that if it's very small, then this if rho and d are small, so d is the sample size, rho is the correlation. If they are small, then we will have a large bound. If the dimension is large, we also have a large lower bound. If k is large, then of course that helps. Okay? So let's interpret this. So one thing that you can see immediately from here is that if the dimension is less than log n over rho, the sample size is less than the dimension over rho. Okay? So this is the kind of range that we are interested in. Dimension is huge, and sample size is very small. And it looks like this is where the interesting things happen. So if the dimension is less than log n divided by rho, then the k must be something like root n. And the size of the set must be at least root n, very close to that. Otherwise, forget it. Okay? For small sample size, this is the best you can do. Okay? If the sample size is less than log n, less than the size, then you can only detect at massive attacks. On the other hand, there's a sharp transition when D becomes much larger than this one. When D is larger than 1 over times, then all of a sudden we can detect very, very small. We can achieve a small risk even when K equals 2. So there seems to be a phase transition at this samples. When the sample size hits log n over rho, then all of a sudden detection becomes much easier. Before that, we cannot detect attacks of size smaller than the square of that. And after that, we can already detect tiny thing, but the smallest possible. And what's interesting is that this type of attacks, when K is written, and even the D equals 3 is sufficient. So if there's only one observation and the K is zero, then we already have enough information to detect an attack. So it's interesting. If the sample size is less than 1 over rho, then having multiple samples doesn't happen. Basically, up to constant, we have exactly the same information from one sample, but from long over sample. But the phase transition here, when the sample size becomes larger than 1 over rho, then everything changes all of a sudden. So I find this kind of fascinating. And these things seem to happen in this kind of problem. Okay? And so how can we achieve this? Well, there's a very simple test that achieves this. This is based on a scan statistic. Scan statistic, this is a very natural test. We scan through all possible subsets of size K and calculate empirical correlations over those sets. And so what we do is that we pick out for all possible subsets of size K. Let's say we know in advance the value of K. That's not a big issue. So if we know in advance the value of K, then we can just go through all sets of size K, and within set we can look at the empirical correlations. If there is an attack, then there will be a set with a large correlation. This is a scan statistic, and you can see that under the alternative hypothesis, the expected value of this guy is rho of this one. We have 3 times K choose 2 members of the sum. So under the alternative hypothesis, the expected value of this is greater than d K squared rho half. Okay? Under the non-hypothesis, well, this is just something depends on the distribution of the standard Gaussian, which we can have. So if we threshold around half of this expected value, then we achieve what I call this near optimal behavior. Okay? So the proof is easy. It's based on the analysis of these Gaussian quadratic forms. Concentration inequality for Gaussians. Okay, that's behind this. All right. Another problem that this test has the exact same computational the computational time that this test requires is n choose k, n to the power k. So it's exponential in k. So if k is not too small, well, if k is 2, then this, like in some cases, then this is k is like square root of n or something like that. Forget it. Okay. So there's not much we can say about computations. There's one thing which is a test that runs well, we can cook up lots of tests that are in real time, but their performance is never close to the optimal. Okay, so we could only come up with one range of the parameters in which we were able to cook up a test which can be calculated in polynomial times, and this is the range when the sample size is proportional to the length dimension. Okay? Well, this is an interesting range because of what I meant here. Something interesting happens, so this may be an interesting if the sample size is greater than this, then we have nothing. Okay. So what's the idea behind this test? Well, the idea is, if we go back to the motivating representation here, you see, over the contaminated set, we have this common signal. All right. This common signal can be anything because it's zero mean. But for some of the samples, this common signal will be larger than a little bit larger. Okay. So if we could identify those guys, where those times in which the common signal was larger than usual, then we could detect anomaly behavior. Yeah, that's the idea here. So in this test, we don't compute empirical correlations like this. We only look at values of the individual components, but we look at for the subset of time instances, these are large. And this is where I assume that we have very few samples, at most logarithmic, because now I can enumerate in polynomial time all subsets of time, let's say, alpha times. Okay? So I look at the largest possible. This can be computed quickly because you can just order these values. So once for each fixed A, I can maximize this because the values of the components over which this is maximized, well, that's just ordering. Okay. So this, if I can enumerate all the subsets of time instances with alpha d elements in polynomial time, and I can do that if d is only log n, then I can calculate this. This test is, you can analyze it, and turns out that it has almost the right behavior. So if rho is greater than log over d, remember this was where things happened. This was the range when things were interesting. Then this test will work. Okay. This constant, well, that depends on alpha, and this value of alpha, that depends on our computational power. So there's a direct conflict here between performance and computational time. And it would be really nice to have some theorem that says that there's a fundamental conflict between these, but I don't know. In this example, yes, it looks like the more computation you're willing to put in, the better you can do. In terms of risk, there might be something fundamental out there, which I don't know. And again, if it is much larger than log, I have no idea. I have no idea what we can do if we want a near optimal test. Okay. One can come up with other very, very simple tests, which are surprisingly sometimes even in some ranges of the parameters. So this test is for the squared number. You look at all vectors, look at the squared norm. The intuition is that the squared norm of such a Gaussian is a little bit larger than the squared norm of a standard Gaussian. So you can analyze this, and it turns out that if k is large, sufficiently large, this test is good. Okay. So this test even beats the scan statistic when this number here is large. So when k is sufficiently large, then this is even better than the scan statistic, which is good to know. So for massive effects, you can calculate very easily a near optimal. Is there an it is large. So if this is somehow threshold. Sometimes this is the threshold when this test is beating the scan statistic. Okay. And it looks like we went through all possible ranges of the parameters, and it looks like one of these two tests is always optimal in terms of risk. So either the test scan statistic or the test based on this squared sum test. One of these two is always good. Okay? And this is where the threshold is. Up to logarithmic factor. So we don't have the complete picture, but we are close. And this is, I find it a little bit surprising that the likelihood ratio, which is ugly, complicated test, can be approximated in basically all ranges of the parameters by one of these two simple tests. Well, one of them is really simple because it's even computationally simple. The other one is conceptually simple but not computational. Okay. Now, in the rest of the talk, I will talk about something which was motivated by this statistical problem, which was very fun to work with, and we had a lot of fun. And at the end, we could even say something about the statistical problem, and vice versa. So this is something about random that comes up when you think about problems of this type. And you realize that these random graphs are intrinsically interesting, and we could say something using statistics in random graph theory and vice versa. So let me tell you about this problem. So for the testing problem, what you can try to do is we look at our satellites here, and we can measure the pairwise correlations between these two, right? Between any two, and we are looking for a small subset of these satellites such that the correlations are large. Okay. So what you might try to do is that we can say that we will define a graph by drawing an edge between two satellites if their correlation is larger than usual. Okay, what do we mean by usual? For the purpose of this talk, let's just say larger than 0. Okay, if under the null hypothesis the correlation will be exactly 0, so let's say we just threshold at 0. Okay, and let's get a random graph. Okay, so the question is, what does this graph look like under the null hypothesis, and what does it look like under the alternative hypothesis? Okay. Under the alternative hypothesis, we hope to get a large, fully connected subset. Because if we see that, then we have reason to believe that there's this dominated set. Okay. Now the question is then, how likely do these fully connected sets to appear under the null hypothesis? Because these may just appear by chance. Okay. So the question is, when we see a large clique, a large fully connected subset, is that by chance, or do we have reasons to believe that there's really an attack? Okay. So that's this. Right. So we calculate the empirical correlations. We normalize. Okay. And define this graph. Okay. Let's say we threshold at 0. You read the paper and we threshold at other values. It becomes much more messy. But let's say we threshold at 0. And as I said, but the question is, what is large? What's the largest clique size that that's reasonable to expect under the null hypothesis? If there's no, what's the size of the largest clique? Alright, so what is this graph under the null hypothesis? Well, this graph is something that's very well studied in graph theory, in random graph theory. This is just a random geometric graph. So what's a random geometric graph? We throw down endpoints, let's say in RD, and we connect at random, and we connect 2 points if their distance is smaller than a certain threshold. Okay, so this is a random geometric graph. Something like this. Maybe this is good. Okay, this is a random geometric graph. We just throw down n points at random, and we connect two if their distance is less than some predefined threshold. Well, we have exactly the same thing here. Why? Because now we are on the sphere. When we normalize xi divided by storm, that's a uniformly distributed on the surface of the sphere. So you can think about this as we have points, random points, uniformly distributed points on the sphere, and we will connect two of them. If their inner product is larger than 0, that just means that their distance is less than square root of 2. Okay? So this is a random geometric graph. Okay? On the surface of the sphere. What's the difference from usual random graph theory? Well, that here d is large, the dimension, which now dimension is what was sample size before. Okay, so here now my points correspond to the satellites, okay, and d is the dimension. So this is why I flipped at the beginning, but now we can go back to the usual notation. So n now is the number of random points that we throw down, and we are on the surface of the d-dimensional sphere. Okay? And we have this random geometric graph. But d, the value of d is, well, we saw that the interesting values are log n, or maybe a little bit larger, in that range. So d is large. It grows with n. So this is a high dimension problem. And in the theory of random geometric graphs, these type of graphs were typically studied when d is fixed. D equals 2 or 3 or a fixed number. And these random geometric graphs are very well understood when d is fixed, but not when d is large. Okay? All right. So I have to tell you a few words about how theory studies clique numbers, the size of the largest clique of a random graph. This is the famous probabilistic method that was so successful in the theory of random graph, in the theory of graphs, and which actually gave rise to the whole theory of random graphs. So, take a finite graph, no, any graph, not a random graph, just any finite graph with n vertices. A clique is a fully connected subset of vertices. Okay? The clique number is just the size of the largest clique. So this is the number that we're interested in. Okay? We can also ask what's the largest independent set. So a set is independent if a set of vertices is independent if there are no edges between them. So for example, these 4 will be an independent set. Okay? Because there are no edges whatsoever among these points. So you can also ask, what's the size of the largest independent set? Okay, this is called the independence number. Now clearly these two numbers are in conflict. You can feel that if there are lots of edges, then your likelihood to have a large clique. If there are very few edges, your likelihood to have a large independent set. So the question is there a graph such that there's no large clique and no large independent set? This is an old question. What's the smallest possible value that the maximum of these two numbers can have? And this was answered by Paul Erdős. And this was basically the pioneering paper that gave rise to the whole probabilistic method. And he showed, but there were all kinds of conjectures before that this cannot be, this is always larger than square root of n, and things like that. And this result came as a huge surprise. But there exists a graph such that both clique number and both independence number are small, very small. They're only like 2 log n, even smaller than that. Okay, and even today, nobody can construct such a graph. Okay. Erdős's idea was that take a random graph. You pick one graph randomly and look at it. And I will show you the whole proof because it's just one slide. It's easy. So let's pick a graph randomly on vertices, and let's look at the clique number and the independence number. Okay. What does it mean that we choose a graph randomly? Well, then every edge is there independently with probably 1/2. Okay, if I pick among all possible 2 to the n choose 2 graphs, then this will be the key feature of a random graph. Okay. Okay. Now then we can just calculate how large. What's the expected number of cliques of size k? This is easy to calculate, because if we fix k points, right? If we fix any k vertices, then what's the probability that they are all connected? Well, that's just 2 to the minus k choose 2, because that's how many edges are there between them. And there are n choose 2 possibilities. And because of the linearity of expectation, this is the expected number of cliques of size k. Okay. So what's the probability that this largest clique is smaller than this? Okay. Well, this equals the probability that there's no clique of size k. The number of cliques of size k equals 0. That just equals the probability that the clique number is less than k, which I can write as 1 minus the probability that the clique size is at least 1. And now I can just use Markov's inequality. This probability is less than the expected value divided by 1. Good. But I know what the expected value is. You see, easy, easy, easy. Markov's inequality is the only inequality. The probability that the clique size is less than k is always greater than 1 minus that expression. 1 choose k times 2 minus k choose 2. And if I put in k, this value of k in here, then what we get is that the probability, at least 1/2, there's no clique of this size. Okay. In a completely symmetric way, we can also prove that there's no, with probability at least greater than 1/2, there's no independent set of size smaller than k. The intersection of these two sets is non-empty. Both of them at least probably 1/2. That means that there exists at least one graph. If you choose randomly, then with positive probability, both of these will happen. So there exists at least one, such that the maximum is less than this. And that's Erdős's proof. Okay. People were completely baffled at that time. And from this time on, Erdős had a habit that he was sitting at the graph theory conferences, and somebody would say a conjecture in the meeting, and at the end of the talk, Erdős would raise his hand and say, well, almost every graph is a counterexample to your conjecture. So this is the type, because it's not happens with probability, with positive probability, but if you add rules, then these probabilities will be actually very close to 1. So actually almost every graph are like this. Okay. But still, we can't construct such a graph. This is called the first moment method. Okay. Using the second moment method, you can actually show that the clique number, this is the correct value of the clique number. The largest clique is actually around this size. If you take a random graph, then the largest clique is 2 log n minus 2 log n. Okay. And today, lots of things are known about this clique numbers. For example, we know that these are extremely concentrated. So the clique number is concentrated with probability tending to 1. It's concentrated on 2 possible values. Okay. Okay. Now, this type of research gave rise to the theory of random graphs, because so first random graphs were used to just study extremal graph theory, properties of extreme graphs, but then it's very soon Erdős and Rényi realized that these were really interesting objects in themselves. So the basic model of what we call now the Erdős-Rényi random graph is that we have n vertices, and we connect two vertices with probability p independently of each other. This is the GNP model, and this is Erdős's favorite co-author for this topic. Okay. The random geometry graph is just what I said. Is a completely different type of random graph. Here we have geometry behind. We throw down n points, and we connect 2 if they are close to each other. This is also random, and you can ask lots of interesting questions. But now, as I said, we're interested in the behavior of these graphs in large dimensions. Okay. So this is just, again, the definition of a random geometry graph that we are interested in. So we have n points on the sphere in dimension b. So in the b-dimensional sphere, we throw down n points, and we connect 2 if their inner product is at least is positive, or equivalently if their distance is less than the square root of 2. Okay? And I will denote this graph G bar n d 1/2. Okay? So G n 1/2 was the Erdős-Rényi random graph, and now we have this dimension. Okay? So the question is, for example, what's the clique number of this graph? Now, it's really not difficult to prove that as the dimension grows, then this random geometry graph will look more and more like the Erdős-Rényi graph. And this is true in a very, very strong sense. So we can define the total variation distance between two random graphs. Okay? Which is simply, we compare for each fixed graph, we can compare the probability that the Erdős-Rényi graph equals this graph and the probability that a random geometry graph equals this graph. Okay? And we can look at the worst possible graph and look at the difference. And this is the total variation distance between the two probability distributions, the distribution of the Erdős-Rényi random graphs and the distribution of the d-dimensional random geometric graph. And if we fix the size of the number of vertices and let the dimension grow, then what this theorem says is that the geometry disappears. So as the dimension becomes large, there's no geometry anymore. These connections become completely random. Okay? This is somehow intuitive. Okay. The proof of this is easy. I will skip it. It's just using the multivariate central limit theorem. You can prove it easily. Let me show you some pictures of random geometry graphs. So this is n equals 50, and so that we see better, I don't threshold at 0. I threshold such that the probability of connection equals 10%. Okay? So the threshold for connecting 2 points is set such that the probability equals 10%. So this is what it looks like if I throw down n points on the two-dimensional sphere. Okay. You don't see too much. This is what we have when we throw down 50 points on the three-dimensional sphere. Of course, I project on the first two coordinates, but you can feel the geometry here. Okay? You can clearly see. This is for 4 dimensions. You can still feel the geometry a little bit. 5 dimensions, maybe. Now in 10 dimensions, this becomes a mess. This is really random. 30, 100 dimensions, this is really a random geometry graph. A fully random graph. 500 dimensions, you can't tell them apart. Okay? All right. So this is kind of intuitive and interesting, but it doesn't answer our statistical question, because we want to know that for a given n and d, how large clique numbers are the clique numbers that we can expect. Okay, so what all we know now from this theorem is that the clique number will converge to this guy. As if we fix n, then the clique number as d goes to infinity, well, because the total variation, because this total variation distance is such a strong notion, from this this implies that any graph property that you might be interested in will converge to the corresponding graph property in the Erdős-Rényi graph. So in particular, as the dimension goes to infinity, the clique number will converge to something like this. Okay? So the question is, yes, but how does d have to be such that we already see this? Okay? Now if we let d depend on n, when will this type of behavior start kicking in? If d is fixed, let's say we are in 2 dimensions, and I throw down lots of points, and remember, the threshold is large because now I will connect 2 points with probability 50%. With probability 1/2, I connect any 2 points. So this will be a very dense graph, and clearly, in any, if I take a not too big ball of fixed size, then everybody in here will be connected. So when d equals 2, then this omega n 2 1/2, or n d 1/2, which is in d dimension, when d is fixed, then this is of the order of a constant, of the constant times n. It's linear. We will have a linear fraction of the points will be fully connected. Okay. So when d is very small, the clique number is huge. It's linear. When d is infinity, then the clique number is only logarithmic. So where does what happens in between? So here's a bunch of results. So as I said, when d is a constant, then the clique number is linear. As soon as d grows, it doesn't matter how slowly, the clique number is not linear anymore. It's not difficult to see. The clique number will be little o. Now if d is little o log n, then the clique number is still very large. It's still very close to linear. Okay? So when d is less than log n, then we still have huge clique numbers. The next step is when d is log squared n, then there's a drop. There's a significant drop, and we can show that the clique number is only logarithmic in n. And when d is something like log cubed, then we already have a same kind of behavior as in the limits, 2 log n. And if d is like log to the 5th, then this really looks like it. Okay. And for a while we were wondering what happens in between, because the big jump seems to happen here. When d is little of log n, then we have almost linear clique size, and when d is log squared, then we have polylogarithmic. And we used the lower bound for the detection problem on the first slide to prove that the clique number is larger than this expression. And what this shows is that the real transition is at log squared n. So when d is less than log squared n, then this is still large. Then this is still grows faster than any power of logarithm. So somehow the big jump seems to happen when d is log squared n. And interestingly, we used our lower bound from the hypothesis testing problem to prove this. Why? Because okay, I have to skip the proofs. Let me just say this: that the last lower bound follows from this intuitive fact that if the clique number for this random geometric graph was very small under the null hypothesis, then I can detect very easily an attack which is larger than that. Okay? So then the risk of the optimal test will be small. But we know, because of our lower bounds, that the risk of the optimal test cannot be small, and this gives us a lower bound for the clique number. Okay? And this is how we could prove that in fact maybe the most interesting transition here happens when the dimension is something like log squared, which was very unexpected for us. Okay, well, some pictures here and some references. So thanks very much.
I was wondering whether to consider the random matrix theory as a framework to analyze the situation.
Yes, and so I actually wanted to mention that, but didn't have time. I think that's what should be the next step. So this whole thing is somehow, especially when we want to come up with computable tests. I think what could be potentially useful is to look at spectral properties of the sample covariances. I don't know. So somehow this whole problem is very closely related to something that's known as the hidden clique problem, which is a notoriously difficult problem that's been studied a lot in random graph theory. So let me just say it. So I show you a graph, and I hide a clique of size k in this graph, but I'm not telling you where it is. And I throw down edges with probability 1/2 everywhere else. Okay? So the question is now, you have to tell me whether there's a clique there, or maybe even find it or not. Okay? So if you have to tell me whether I hid a clique or I didn't hide a clique of size k. Now clearly, if k is larger than this 2 log n, which is the size of the largest clique, then this is possible. Well, this is possible if I have an infinitely powerful computer, right? Because then I can just compute the clique number. The problem is that computing clique numbers is one of the most difficult computational problems. Even approximations are NP hard. So the best that's known in polynomial time is to detect when k is something like root n. This is the best possible. This is the state of the world. And then there's also no fundamental lower bound that shows that this is the smallest. And this is actually achieved by spectral techniques, by looking at the eigenvalues of the corresponding of this graph, so of the adjacency matrix. So yes, I think that's a good way to go, but we haven't.
Consider the case where you don't have a diagonal graph, if you don't have IID data, is it possible to go for similar analysis?
You mean that the null hypothesis is something else? No. Yeah, there are many ways to. Yeah, that's one of the directions that you can go to. Other is to drop the Gaussianity assumption. I don't know. We really use heavily everything that's about the Gaussian and the standard Gaussian. Yes.
So can you say something about the detecting S for recovering YC, recovering the city?
Yes.
They can actually find it.
Yes.
So in your structured settings, you find S.
Yes. We haven't looked at it, but I suspect that the possibility of estimation is. I think it's a harder problem. It's really harder than just detection. There is some work in a related setting when instead of detecting correlations, you want to detect whether the mean is elevated in a small subset. Okay. So now so everything is still independent, but there's a small subset of the components where the mean is a little bit larger. And in that setting, it is known that actually identifying where the mean is larger, that's strictly more difficult than just detecting whether there's a subset. And I suspect that something like this should be true here.
One last question. Regarding the first part of the talk, so I'm not sure I understood exactly how all the values relate, but can you show a gap over this? Because there seems to be a gap of more than constants between what you can get with efficiently computable methods and inefficiently computable methods?
So it depends. In some ranges of the parameters, we've got the squared norm test that's right, not all, up to a constant factor. And in some other ranges, we have nothing. And there's that middle range, when that little test I showed you, that gives up to a constant factor an optimum test. But in some ranges of the parameters, we're completely off, and we have no idea what to do. And that's typically when k is large but not too large. It's much smaller than root n. Let's say rho is a constant. I have no idea what to do. Okay, computation.
Can we just clarify